So this is going to be a reaction that is completely based upon two concepts that you became aware of in Organic Chemistry 1. If you simply apply those two concepts together, this should be, well, maybe a little bit of a concept from sort of this semester, but not really. It's mostly Organic 1 concepts. And again, I showed the acetic acid in there to sort of help you guys potentially think through this. Technically, you don't need acetic acid for this, but it does make a point that I'm going to make in a minute. These will react together even without acetic acid. Thoughts. So what's your name?
Olen?
Olen?
Yeah.
Olet with a T or an N?
Onan, like Conan the Barbarian.
Onan. All right. Conan. Onan the Barbarian. All right. So what do you think?
So what I did was I put a protective group on the ketone.
It's not a synthesis.
Not a synthesis.
No, we're not asking for synthesis. I'm giving you a mechanism. I'm basically saying that you take acetone, right, and you mix it with bromine, and acetic acid can help with this a little bit, but pretty dead. Yeah, so the first concept of this is keto-enol polymerization, right? So we know that the ketone will go to keto-enol polymerization, and this is part of the reason why I put the acetic acid in there. It can sort of be used as a proton source to sort of go from here to there, right? If we want to use the acetic acid as our source, right, the way that we would get there, right, is by protonate this bond, because we've been doing that quite a bit. Right, and then you're going to regenerate your acetic acid through an elimination reaction. So that's, if you want to draw through the keto-enol polymerization, you can do that, or if you sort of recognize the keto-enol polymerization, you just want to sort of say it, that's fine, as long as you actually know what's going on here. And now you're basically at the enol tautomer, and the enol tautomer has now effectively has changed the functional group, right? It's changed the functional group from the carbonyl, which we think about as being electrophilic, right, into an alkene, and not just an alkene, but an alkene that we'll see is actually fairly nucleophilic. And given the fact that we have bromine as our electrophile, having bromine react directly, having one electrophile react with another electrophile might not necessarily be that obvious, but the enol form is in fact nucleophilic, right? And so we've seen this reaction before, right? This is one of the classic Organic 1 first semester reactions where alkenes react with bromine, right? And how do alkenes react with bromine? There's various things that we can do here, all of which would be fairly reasonable. What I would probably do is, when we think about bromine and alkenes, we think of that bromonium ion a lot. So let's go to the bromonium. Right, so we're sort of at this bromonium ion. And from here, there's a few things that we can do. We could have the bromonium ion attack and get the dibromide. That will eventually break down to the product. I think the easiest way to see this is to think about the resonance form, right? Because the moment that you do the sort of that open resonance form, right? We see that that's the open resonance form, or not, I don't know if you want to call it resonance form or not, but it's the open form. Resonance out of this. More like the resonance form is over here. We have the Br minus left over. It's going to deprotonate that. Okay. So so this is a reaction that I think I want to show for a couple of reasons. It's a nice way to start off talking about enolates and enols and the nucleophilic behavior, right? Because this is what we're going to talk about a lot today. Is this is an enol, and so we're going to talk a little bit about how enols are kind of like nucleophilic alkenes, right? They're nucleophilic sources of alkenes. I think it's also just a nice example of a new reaction that's simply based upon old concepts, tying a couple old concepts together, right? We knew about the enol-keto tautomerization. We knew about bromine reacting with alkenes. You tie those two together, and you get this reaction here. I also like to start this one because I always like to tell a story. So I've got two stories about this specific reaction. The first one is a story about a friend of mine. So grad school can be stressful, right? And you kind of don't want to embarrass yourself in your first year. And so, and grad students often in their first year, second year, sometimes throughout their whole PhDs, they end up teaching. That's why a lot of you guys have recitation instructors that are sort of teaching. It's a good opportunity to, for them to sort of interact with students and teach and sort of solidify their foundation. So anyways, I was downstairs teaching a lab, and one of my good friends comes down, who I had lived with at the time, and he comes downstairs, and he's got a completely different change of clothes on. He's got like a jumpsuit, and it's like a women's jumpsuit, right? I think maybe I made that up. It was definitely a jumpsuit. I think he borrowed it from, I don't know if it was a woman's or not, but it was a woman's jumpsuit. I don't know if it was actually, jumpsuits can be whatever. They can be, there's no, whatever, gender neutral, let's say. But he was wearing one that was of a woman in his labs. And he goes up to me and he goes, because we'd often drove home together and he had to run home. He goes, you know how there's those showers that nobody ever uses ever? Because I had to use one. And what he was doing was he was running a reaction with bromine. And when he was done with the reaction, he dumped it into the waste, not really thinking anything of it. And as you guys know from the waste that you often use, right, what does that waste have? Right? It's got a lot of acetone in there, right? Because as you guys know, you're always washing your squirt bottles and everything with acetone. So the waste bottle that he had a whole bunch of acetone in it. And what does the waste bottle often have? Other stuff, which could include a little bit of acid in there. And the acid will basically help drive the equilibrium in this direction. If you look at what's left over, HBr, right, that's going to further hasten this equivalent. And so he dumped this sort of bromine into the aqueous waste, and as he was leaning over, it like sprayed everywhere and got all over him. So could have been a disaster. Instead, it's a good story. So that's story number one. Yeah? No, because the H of the HBr is the electrophilic source. Right? That would hit the H there. Right? Okay, so that's story one. Story two, so I had known about this, and when I was doing some of my research, I wanted this for some reason, and it ended up not working out, but I wanted to make this molecule. You could buy this, but this was the most annoying thing. This is cheap. I could have bought this, but I was working out a synthetic scheme to make this one molecule, and I was showing it to one of the senior grad students, and he goes, oh, there's this Orexin prep. Orexin are like these very thorough, we actually just submitted one recently, they're very thorough methods that are like very in-depth. They also have to get checked by somebody else at a different lab to ensure that the chemical yields and everything are reproducible. So it's just a very thorough journal for synthesis of reagents that are really valuable that people would want to be able to do and want to be able to reproduce. And so I'm following the procedure, and the procedure is I took some of this, and I think it was like maybe a catalytic amount of iodide or something like that. I forget exactly what the procedure called for. And it's heating. So I was kind of surprised, right? Because you're sort of, my buddy had just had this happen in the waste, right? So I thought you wouldn't even need that. You would just add acetone. And so I did the reaction. You heat it up a little bit, and then there's like a distillation, because you end up getting not just this, You can sometimes get like dibromination, tribromination. So towards the tail end, you have to sort of distill each of these away from one another, which is pretty involved. Okay. So when I'm all done and I have the cut of the distillate that I want, I take it out of the hood and I go to weigh it out, right, in my Terran flask, and my eyes just start watering. Scariest thing I've ever experienced in a lab in my life. You gotta be careful. This is a lesson of being cautious and knowing what, not just what your starting materials are, but potentially what the products are as well. But I took it out and I weighed it out, and I just, tears just streaming down my face. Not knowing what's going on, I take it, I put it back in the fume hood. This is an insanely potent lacrimator, like onions, and I didn't know that at the time. It's also very volatile. Okay, so this had basically, I had made this, I guess I made it well, right? But basically, it just made me tear up and just gushing water down my eyes. Like imagine onions times 100, right? If you've ever started crying with onions, imagine just that, but and there's very little scent to it as well. So it's weird. But just, I guess that's a word of caution. No, did I? I may have, I don't remember. But it's not, it was fine once I put it away, it went away. It's kind of like onions, right? Like if you're cutting the onion and you start crying, it's not like you're then crying for the next hour, right? Like once I put it away, I got better fairly quickly. But it was scary. Huh? No, I don't think so. They probably use other stuff, because this is also a really good electrophile. And a lot of times really good electrophiles are also really good carcinogens. Oh, nice. Right? Just because they'll nucleate, because your DNA and stuff is just like one big nucleophile, and so you start doing modifications to those and it can be bad. So you probably don't want, I'm not worried for the limited time that I was exposed to it, but it's not necessarily something that you would put in something that would be exposing to people all the time. But I could be wrong. It would depend upon use. So anyways, so there's a couple nice stories to start your Wednesday. And now you'll never forget the reaction of bromine with acetone. Okay. All right, so today we are going to talk about the reactivity of molecules that are like this. This is an enol, right? So we're going to talk about enols, we're going to talk about enolates, we're going to talk about enamines. What's important to recognize, right, is that there are, in principle, two nucleophilic sites on this molecule, right? We have our alkene, which can be nucleophilic, right? We also have the oxygen that can potentially be nucleophilic. As we'll see, both of those can potentially happen. Actually, as we won't see, we're going to focus pretty much squarely on the carbon-based nucleophilic source to keep these simpler. So there is this sort of dynamics where you can have the two. Maybe I'll bring it up in an example of where sometimes you can go O-alkylation versus C-alkylation, but primarily what we're going to see is chemistry taking place at this position. And what that means is that when you have ketones, esters, as we'll see, when you have this beta hydrogen, right, next to a sort of this, sorry, alpha, I should say, if you have this, a proton alpha to the carbonyl, right, you can begin to functionalize that position. So ketones, esters, and so forth, these carbons, as we'll see, can basically serve as a new nucleophilic carbon source, right? So we've seen examples of nucleophilic carbon sources in the past. We first saw them with acetylides, right? Triple bonds being good sources of carbon-based nucleophiles. We then saw how, like, alkyl halides could be converted into things like Grignards and alkyl lithiums to be used as nucleophilic carbon sources. Ketones can often serve as really good sources of nucleophilic carbons as well through their conversion into enols, enolates, and as we'll see, enamines. Okay? Yeah. Here? This double bond? So as I sort of mentioned, when I was running this reaction, use a catalytic amount. I think I was using, I don't remember, but I thought I used like a catalytic crystal of, and I think you guys did this as well in one of the earlier labs. Like you used iodide along with some other, and the iodide basically serves to promote the formation of acid. Once you have some acid in there, it's not that these won't go, but it accelerates this interconversion, right? So in principle, kind of what you're describing by having the bromine attack this double bond could eventually lead to the formation of HBr, and then the HBr would help accelerate this, right? But I don't want to complicate it more. There's lots of, when we're looking at reactions, right, I think what we'll hopefully see, right, and this is part of the idea behind reaction mechanisms, you guys are often asking, well, can I go in this direction? Well, can I go in this direction? Reaction mechanisms are sort of mazes, right? When we're going through the reaction mechanisms, there's lots of outcomes, and part of this is sort of understanding and recognizing all of those, but also recognizing that lots of reactions are reversible, and that when you see a product, you navigate that maze, if you will, to eventually get to the product, hopefully through a series of arrows that are legitimate. Yeah. What's that? It's a good question. I don't know off the top of my head. I would imagine it probably could be, but I'm guessing it would be. I don't know off the top of my head, so I don't want to tell you one way or the other. But this is the classic, right? The thing with chlorine, right? The thing with Cl2 is that chlorine, when we're talking about electrophilic sources, we don't use Cl2 nearly as much as we use Br2, and that's a lot of the times when you guys start asking questions about whether bromine translates to chloride or Cl2. It's largely because Cl2 in a synthetic organic chemistry lab isn't nearly as widely used as bromine, and that's for a couple different reasons. As we've seen, a lot of times when we put halogens onto molecules, we're using them as leaving groups. And so first of all, bromine is a better leaving group than chlorine. So bromines can oftentimes be much more useful as electrophiles just because they're more reactive, right? And so that's one of the reasons why. The other thing is that so bromine is a liquid, chlorine is a gas. Right? Cl2 is a gas. And so from a practical standpoint, working with bromine versus working with chlorine, chlorine's also a lot more toxic. They're both toxic, but given the fact that it's also a gas and it's toxic, it's a lot more dangerous. They both have their concerns, but chlorine is just technically more challenging to work with, and it happens to be a bit more challenging. So a lot of times when we see this chemistry, we'll occasionally talk about Cl2, but this is also one of the reasons why I'm not as familiar, but I would imagine, but yeah. You're talking about radical-based halogenation. Yeah, you're talking about radical-based halogenation and sort of that, yeah.
So it's the acid. The acid is basically driving the carbonyl to be
Right. So the mechanism through which you could imagine enol keto tautomerization. So this is Le Chatelier's principle driven, right? The equilibrium between enol keto tautomer, right, favors the ketone substantially. However, to accelerate that interconversion, the faster that can happen, the quicker you're going to generate this, and the better the reaction is going to work. And so having a little bit of acid in there can help accelerate this process.
But it does make the carbonyl more nucleophilic, because usually you would think that carbonyl is electrophilic, right?
Correct.
Yeah, but because the acid is in there, it changes its nature.
Sure. I think I see where you're going. Sure. It's not necessarily as simple as that. Could an acid blunt? I mean, what's the nucleophile? Right. I mean, what about like an alcohol? Right. An alcohol can be a nucleophile, right? In principle, right? Or it can be an electrophilic source of the water leave. It's just a functional group. The conditions of the reaction are going to alter what that are. So is it the acetic acid? Is it the fact that we're not treating with nucleophile, we're treating with the bromide, right? So, right, does that make sense? Right? I mean, in principle, once we protonate that at that intermediate, we have an activated molecule there. So you could certainly imagine a mechanism where the acetate would add in. Now that's going to be reversible, but again, it would be the carbonyl reacting as an electrophile. So it's just about the conditions of the reactions, and it's a little bit more complicated and I don't think it can be distilled to what you said, but there is some truth in what you said.
But so Br2 is considered like
a good electrophile. Oh my god, yeah, bromine is a fantastic electrophile. All right, moving on. Yeah.
What the hydrogen for the bromine for the
What's that?
the
like eliminate?
Yeah.
Yeah, then you would just get to the enol, and that could then eliminate. That would ultimately lead you to the same product as well, right? And in fact, you know, as I sort of said, this isn't the only product. This reaction can be kind of, you can get a mixture, right? You can get dibromoacetone, you can get tribromoacetone, and those would all go through similar intermediates that you just described, right? Because then you would have the enol here with a bromide on it. So you'd basically be on this with a bromide on it. So yeah, and so this is why additional things can keep happening, right? Which is why it's not the, you know, it's, you can get lots of things. All right, let's, so again, nice little intro to enol chemistry. For the most part, you know, when we're talking about, you know, enol chemistry, you know, there's a couple different ways that we can think about this. Let's just start with, I guess I'll just start with a simple sort of aldehyde, thank you. Right? And, you know, depending upon, you know, this is something that depending upon how we run this reaction, sort of the reactivity of enols can be, or this sort of enolate type reactivity can be, like we've seen in the past, it can be mediated by acidic conditions, it can be mediated by basic conditions, and so there are these two possibilities. And one of the sort of basically classic examples right, of sort of acid-mediated chemistry is something called an aldol reaction. Okay, and as we'll see, aldol chemistry can be carried out. I'm just going to start with it under acidic conditions. We'll show it under basic conditions as well. But so, aldol. Right? The aldol reaction has its name in the fact that it's an aldehyde making an alcohol, right? And so this is just a two equivalents of this are going to make one equivalent of this molecule. And if we think about this reaction, you know, it's not going to be too dissimilar to what we just saw with bromine, right? So as you might imagine, the first step, right, of a as you might imagine, the first step of this reaction, right, can be invoked based upon the sort of enol keto tautomer. I'm just showing as one stereoisomer. I'm not implying anything there, although we'll see that maybe if we have time, we'll discuss some of the stereochemistry involved in aldol chemistry. Okay? And so now we have our nucleophile, and the aldehyde is our electrophile, right? And so what can happen here here. Wanted to draw it down there just to be. Right, this is something that we've seen in the past, right? So what we have here, and this will ultimately come back to stereochemistry if we ever get into stereochemistry, although we may save the discussion on this until we start talking about pericyclic reactions. I think we'll come back to the stereochemistry of this process. And basically, what do we have? We have 1, 2, 3, 4, 5, 6. And you don't necessarily have to draw it this way, but it's certainly worth noting, right? That there's that magic number of 6 that we often see, right? And if we start to push electrons, and we've seen this in the past, right? We're sort of doing this 6-membered port chelation, push the electrons around here. Nice little transition state. Or pre-coordination, whatever we want to call it.
You're looking for 6 what? 6 carbons?
six atoms, right? So it's a 6-membered ring, right? 1, 2, the hydrogen bond being 3, 4, 5, 6. And so if we think about the bond, where the bond's being formed and where the bond's being broken, we'll revisit this. We'll start to see something very similar when we get to Pope and Claisen chemistry. But this certainly helps basically drive the aldol condensation, and this is just a redrawn version of this, right? So if I rotate it around, I simply rotate it around that bond, right? You can see that it's that molecule there. Okay, you guys see that? It's a lot of arrows going on there, so if you don't see it, you could alternatively not draw it in the 6-membered if you're struggling to see it that way, although I would encourage you guys to see that. You could also imagine, you could think about it being acid catalyzed a little bit more, and this is a perfectly valid way to think about this as well. Right, with the alkene sort of attacking. So this is the sort of the closed transition state, that's the open transition state. It can actually work through both depending upon conditions. But the important point is you're basically making reverting back to what we were talking about with the bromination reaction. The enol is our nucleophile, and all that we've done now is we're now just introducing an aldehyde as our electrophile. So it's the exact same thing that we just showed you with the bromination, right, of acetone. So it's that exact same reaction, except instead of bromine being our electrophile, the aldehyde is our electrophile. Clear? Straightforward enough, right? Okay, so the one thing about the aldol reaction is that the product that you're forming, right, you can actually imagine that if you simply do, and especially this particularly happens under acidic conditions. So the aldol reaction, if you let it continue to go, or sometimes people will run the aldol reaction, as we'll see, under basic conditions, and then we'll swap over to acidic conditions. Sometimes you don't even need to. Sometimes it's just because the system, it'll do this just based upon thermodynamics alone. But usually we think about this being acidic, where we will squiggle there. I won't really describe the stereochemistry at that point, right? But what you'll do is you'll actually get an elimination, okay? Right? So, the squiggle just means it could have been either way. I'll just draw it, whatever, I'm confusing you guys. Don't plus isomer. Don't read too much into the alkene isomer there. You guys could probably, we could probably guess, this is an elimination that's going to be an E1 elimination. If we went through our sort of knowledge of elimination, right, what we're sort of doing, right, is we're trying to decide between a methyl and a carbonyl, which are spatially very similar. So you can imagine that whether this is on one side or whether it's on the other, those are going to be very energetically similar. And so it might be difficult to get specific alkene stereochemistry in this case. Okay. What do we call reactions when we lose water? What's that? Dehydration. I guess that's what I call it. Yeah. It's not an aldol dehydration, but you could call it an aldol dehydration. And we've also called it a condensation sometimes in the past, right? So the term condensation, dehydration are often used in the same, basically saying the same thing. So when you just carry it to this one, it's an aldol. When you go from here to here, it's an aldol condensation. The whole sequence is called an aldol condensation. So not just the elimination, it's that whole, from here to here is the aldol, from here to here is the aldol condensation. Okay? Clear? All right, so I'm sort of showing here under acidic conditions. Okay? You can also do aldol chemistry using basic conditions. Okay? Can I erase this? So we haven't discussed this yet, but those two protons right there, yeah, Christine? Yeah, so you need the acid, yeah, so there's still H plus there, yeah. Right, because you generate the water, and then the water eliminates. It happens, okay. This is a thermodynamically favorable process. Okay? It's very difficult to go in the reverse. You can do it. Former colleague of mine did a lot of chemistry where she tried pushing it this way, but it's very difficult to go in this direction. This direction is much more thermodynamically favorable because of the conjugation of the system. We haven't really talked too much about conjugation. We'll start talking about it a little bit later on, but when you have these sort of two double bonds that are sort of connected by a single bond, there's a sort of conjugated nature there that we'll talk about. So this sort of alpha-beta unsaturated aldehyde is thermodynamically stable. So you don't necessarily need to push something that would drive the water to leave, if that makes sense. Okay? Okay, so these protons here are fairly acidic. These sort of alpha protons to a carbonyl. The pKa's 21, 22, 23, somewhere in the low 20s. Okay? It's going to depend upon the specific nature of it, but you're talking about a pKa of about, let's say, I'm just throwing that number out there, it's low 20s. I'll throw 22 up there just as an example. And so when you take these molecules and you want to deprotonate them, in general, you are going to basically use the classic base that's used to generate the enolate is something that we've seen occasionally, which is lithium disopropyl amide. So it's abbreviated LDA, so if you talk to any synthetic organic chemist and you say LDA, every synthetic chemist will know what LDA is, right? So this is lithium disopropyl amide, okay? LDA is a choice base, or it's one of the choice bases for enolate formation, largely because the pKa of this, as we know from the acetylide chemistry, right? pKas of these are somewhere around 30, so they're very, very basic. It's also bulky, right? And so you're unlikely to get side reactions that would basically promote that this is going to be a good base, right? It's going to be less likely to behave as a nucleophile. And so for all those reasons, it's a fairly robust choice of base to generate the enolate. Okay. Okay. And something about no, we're not going to talk about this. Maybe later on we'll talk about this. But so now we have a system that's got a negatively charged oxygen, so it's usually got a lithium counterion, right? And now this is a really, really, really good nucleophile. Now I was talking earlier about O-alkylation versus C-alkylation, right? And so, you know, people do occasionally take enolates and they'll trap them with certain things to put a group up here. We won't be discussing any of those. But if you're curious, you know, occasionally, and we don't talk about it too much, it's come up maybe every once in a while, but I don't emphasize this, at least at this level. I think there's other stuff to learn. But oftentimes, selectivity of reactions, remember when we were talking about 1,4 addition versus 1,2 addition, right? If you recall, we talked about, this would be maybe just a good opportunity to kind of reinforce this, right? Remember how we talked about how you've got two delta positives here, delta positive and delta positive? And do you remember, if you want to react here, do you remember what reagents you use? What's that? You'll use like a Grignard, or you'll use a alkylithium, right? And we'll come back to this in a couple minutes. if we want to add to this carbon here, what do we use? We said the cuprates, right? And so the way that we often think about this, and maybe the way that you guys can think about this is we sort of talked about how this carbon right here has the most positive charge to it, right? It's, if you were to sort of look at the electron density map, that carbon would be the most electron deficient carbon, right? And so it would be the carbon that would have the most positive charge to it. And so that positive charge is going to attract things that have high negative charge character to them. So something like a methyl lithium or a methyl Grignard, those are very ionic. And so they'll be attracted to the similarly cationic, right, carbon. Whereas this carbon down here deals with sort of more molecular orbital theory and lowest lying LUMO, which is a little bit, I think, harder to sort of get at this point of this course. We'll talk a little bit about HOMO and LUMO when we get to Diels-Alder chemistry. But so this is usually where the lowest energy orbital would be. So if we think about dumping electrons into wherever the lowest energy orbital is, that's where that would be there, right? So in a similar way, if we think about where the charge distribution is going to be on an enolate, right, the most of the negative charge is going to be up here, right? And so usually when we want to do an O-alkylation, we need a really, really, really sort of almost ionic electrophile in a way. And so we won't really talk about that at all. Okay, but that's just so you know. For the most part, and pretty much all we're going to talk about in this class is the reaction that can be denoted through the sort of less, so this is the resonance form that's the major contributor to the resonance hybrid. This is the resonance form that's going to illustrate how we primarily think about the reactivity of enolates. Okay, and so this, as you can imagine, could similarly now attack carbonyls. Right, and we're going to get to that. This is the same molecule as I just showed there. Following what? An aqueous work. Yeah, right. Okay, so take-home points here. Under acidic conditions, you can run aldol chemistry by facilitating formation of the enol and activating the electrophile. They can conversely be driven by deprotonating the sort of alpha protons to the carbonyl and making that into a stronger nucleophile. All right, does this make sense? Okay. Okay, so I was bringing up this. So these are both aldol condensation. Okay. I was bringing up this molecule here, and so maybe we'll start talking about alpha-beta unsaturated compounds. So I was talking about how you could add an enolate here. Sorry, not an enolate here. You could add a nucleophile here, or you can add a nucleophile here. And as we described, those enolates that are highly charged, sorry, those, I misspoke. The nucleophiles that are densely charged, right, we'll add here because of the charge-charge attraction. Nucleophiles that are not as densely charged, where maybe that charge is spread out a little bit, will attack here. Given that information, if I were to take this enolate and I were to react it with this molecule, where do you think it would react? And why? I'm interested to hear both the answers. I think an argument we made for either, there's a right answer, but let's think about it. Let's use our yeah, Henry. Okay, so I got one vote for the ketone. Why do you think it would be the ketone? So so Henry's drawing the parallel to, which I think I was anticipating potentially getting this answer, right? He's sort of making the analogy, hey, that's like a methyl lithium, right? You know, it's kind of like a methyl lithium, right? It's got a lithium anion and it's got a negatively charged carbon. All right, so that might be an argument to make this one. Yeah,
But
but there's
there's resonance, so it's not.
resonance. And so I think this is a nice example, right, of where, given this sort of knowledge, we may have tried to argue either way. We could say, hey, this is charged. Hey, this one has resonance, so maybe it's not as densely charged. And so then organic chemists run the reactions and they see what happens and they make the argument. So, yeah, so Carmen's right. So it adds here. So enolates will generally add to the beta carbon. So then a question could be, right, why does methyl lithium add to one position and this enolate lithium add to the other position, right? And what differentiates the two is that one has, even though they're both carbon-based nucleophiles, that the anion on one is spread out a little bit more. So we're going to go through this reaction and show you guys what the product we've made. This becomes one of those problems where, hold on, Lee, 1 second. I'll get to you in a second. But we're dealing with a lot of carbons and bonds forming across a lot of carbons. And I'm going to go through this mechanism, and what I want you guys to sort of recognize is that when the functional groups end up getting further away from one another, that's when you have to really heighten your focus to make sure that you don't add a carbon or subtract a carbon, right? So we'll go through this in a minute, but so I just want to sort of make that point, and then we'll go through it. Yeah, Lee.
As you can see, it's because it's less dense.
Yeah, so it's spread out over the resonance form. Right. Okay? All right, so if we were to react with this guy, or systems where we have the alkene and conjugation, right? That's going to attack that carbon, right? And what's going to happen, we're going to push these up here, right? And we're going to generate right? We're going to generate this enolate here, right? This may be an aldol that might be challenging. I'm just showing you as a representative example, because now as you're seeing, now I'm generating a new enolate. What do you think that new enolate can do? Right, it can attack other things. So this is where sometimes control of reagents, addition, things of that nature are important. We'll see that similar type of chemistry ends up becoming applied once we start talking about polymer chemistry. A lot of polymers can kind of be based around polymerizations of alpha-beta unsaturated molecules, because you'll get one of these to react with the second equivalent, which will then generate enolate, and then it'll keep going, and make polymers. And so certainly enolate chemistry and Michael chemistry, because of the fact that you're also generating enolate, can be sometimes challenging to control. In particular, this one probably would not be one that would work out great. Why am I saying that specifically? What we need to do here, right, is we need to make sure that we had only enolate, right, and then treat it with this molecule. Because if we were trying to do it all in one pot, right, you might get some molecule over here, you might get some molecule over there, and even this one might be challenging, because this might then deprotonate this, and so it might become challenging. And so, you know, it's just important to recognize that when we're sort of going through these reactions, there are potential for side reactions. And this is just a representative example of what would happen when this would add in. Assuming that you didn't get any additional, you know, we just did the one Michael, right? The product in this case would then become ketone right? You basically quench that at the end and you can get the molecule that I'm showing you there. So again, I've just shown this with a cyclic enone, but it can be any enone, right?
Wait, where is that in the bottom?
This,
Oh yeah,
you're just going to quench it and protonate it.
okay, the double bond. Or the, yeah, there you
Okay. All right, we clear on this? And so this reaction, if you take an enolate and you treat it with an aldehyde, that's called an aldol. When you take an enolate and you treat it with an alpha beta unsaturated carbonyl, that reaction is called a Michael reaction. Okay, so this is called a Michael. Who's Michael? It's the I can't remember his name. I was going to try to make a Knight Rider joke. Have you watched Knight Rider? Michael.
Oh, God, that was
The car. Yeah, the car that goes, Michael. Yeah. Go. Knight Rider. So why does it go 1-4? So the definition of a Michael. So the only thing that differentiates an aldol versus a Michael is the electrophilic source. They're both dealing with enolates reacting with something, right? The aldol, Fatu, is when it reacts with an aldehyde, right? The Michael, and sometimes people refer to aldols when they're talking about reacting with ketones as well. That's a little bit more challenging, but you can do it. So when you're adding basically to that directly into the carbonyl, right? So an aldehyde or a ketone, that's an aldol. When you're adding into the sort of beta position of an alpha beta unsaturated, Michael Landon, that's his name, right? Michael Landon?
Oh.
Michael Landon was
Little House on
Yeah,
the
no.
Prairie.
Yeah.
No, who's the guy that was Knight Rider? Oh, it's
David
what's
Hasselhoff.
David Hasselhoff. There you go. They kind of look the same. All right. So yeah.
Michael Knight was
Yeah, Michael Knight.
Losing focus.
Fatu ringing us back in. We need that. All right. So yeah, we're gonna add to the beta carbon. Okay.
Thank you.
Yeah.
Can you repeat why it goes to the beta position as opposed to the more positive charge, more like less electrons as carbon of the carbon?
So the reasoning that you could reason why does that go versus, say, for example, a methyl lithium is that the enolate's got that charge spread out a little bit more. So usually when it goes 1-2, it'll be more based upon charge, a tight charge, right? And that's why when Henry said, oh, it'll go 1-2, without knowing the answer, that's legitimate to say that. But after you run the reaction, you see it, you can then, in retrospect, basically say, oh, well, what's the difference between these two? Why would this one go 1? Why would methyl lithium go 1-2? Why would the enolate go 1-4? And you could say, okay, well, based upon what I know, these molecules generally are based upon charge distribution, and so perhaps, given the fact that the charge distribution, right, is more spread out on an enolate, right? And in principle, the charge distribution on the enolate isn't even on carbon mostly, right? It's on the oxygen, right? It's just adding from that position. But I think the easiest way to think about it is just that because of that resonance, it's a more spread out negative charge. Right, does that make sense? Okay, we good? Okay. So there's a lot of reactions that you could imagine sort of doing enolate chemistry into. These are just a couple. All right. Okay, so all right, so we talked about them reacting with carbonyls. We talked about them reacting with ketones, aldehydes. We talked about them reacting with alpha beta unsaturated esters. Okay, so if you have right, if you take a molecule such as the one that I'm showing you here, right? And you react, and you try to react two of these molecules together, right? This may form. Let me just. Right. This is going to be a reaction, another enolate-based reaction. But instead of our aldehyde being our electrophilic source, now we have the ester being our electrophilic source. So as you might imagine, right, by sort of right, so as you might imagine, once we actually deprotonate this molecule and generate an enolate, right, if we're to add this into another equivalent of that ester, I'm just sorry, we're not going to discuss, I'm just going to do that for board space purposes. Right, so you guys see what we're doing here? So we're adding into the ester, and we're basically getting to this sort of charge, effectively an acetate, or a hemiacetal, it's sort of the deprotonated hemiacetal, right? So what's going to happen there, based upon what we learned in the carbonyl chapter? What's that?
So something's gotta be.
Something's got to go, right? Yeah, exactly. So what's going to happen is you're going to get to molecules that look like this. And this ends up being a really good reaction, in large part because once you get to this intermediate right here, this is so we mentioned that the pK of these protons are somewhere around like low 20s. What do you think about the pK of this proton here? Pretty low. Yeah, I think it's 9 sounds about right. Yeah, I was thinking 10, but yeah, it's certainly low, substantially lower. And it turns out that these molecules will sometimes even exist in their tautomeric form. Sometimes when you look at these, depending upon solvent or whatever, these will sometimes even exist as this form that you see here, right? So this is the sort of the enol form of it. Okay, so it's almost like you're deprotonating. If you actually think about this form here, and you think about what you're deprotonating here, right? And you think about these lower pK values, right? What is this? It's almost like in many ways an extended carboxylic acid, right? Because if I were to deprotonate that, right, I could resonate up into a carbonyl. So it's somewhere in between, a carboxylic acid in many ways, and a typical phenol or alpha proton type situation. So much more acidic, and sometimes, as I said, they'll even exist primarily in this sort of enol form. Why would it exist in this enol form? Why do we think? Again, we haven't necessarily gotten to this chapter, but it's something that's come up. It also came up today, yeah. Yeah, so we have conjugation all the way through, from here through the double bond, all the way through the double bond. So we have a nice little array of conjugation throughout that system that sort of makes this a very stable system. For these reasons, so this is called a Claisen condensation. Okay, so again, what distinguishes a Claisen condensation from an aldol or a Michael is simply the fact that the electrophile is an ester. And if we think about it reacting with that ester, we can sort of reason that we're going to ultimately kick out the ethoxide and we're going to get to this molecule that you're seeing right here. Okay. The products of Claisen condensations can be very useful in many ways, in part because of how acidic they are, right? And so if you say, for example, right, let's say, for example, that you wanted to, can I erase this? So let's say, for example, that you wanted to let's say for example that you had this ketone here, right? And let's imagine that we wanted to try to use enolate chemistry with this and then trap it with other electrophiles. One of the challenges to doing enolate chemistry with this molecule is you might get, say for example, substitution over here, as well as substitution over here. So you might get some mixtures of mono and bis that might complicate the reaction. And so one of the nice things about this molecule is that in addition to the fact that you don't need nearly as strong of a base, you can actually get away with things like bicarbonate, like baking soda, right? Rather than LDA, which would be catch fire or burn up if it was out in the air, right? Baking soda could basically, no pun intended, be used here as your source, right? And so what that means, right, and let me just sort of show you guys really quickly, right? If I wanted to make this and then treat it with some electrophile, like, I don't know, what does the book usually use for these? The book likes to use like alkyl electrophile. So let's say, for example, that you want to treat it with, I'll just put alkyl bromide there as just an example. So you want to take this enolate, you want to treat it with a generic electrophile. Right? What we can do here is we can actually, if we want to, we can get to that molecule there using chemistry that you guys know. How do we do that? How would we go from here to here using chemistry that you've learned? Bless you. What's a leaving group? So some testing you guys on, I think something we talked about last class. Something we talked about last class.
Oh, the heat?
What's that? The heat to do what? It's a two-step. We have to do two reactions. We have to do one reaction first. So you're on the right track,
Heat
Lee.
reduces.
No, heat doesn't reduce.
Hey, I should have done that.
Anybody remember? Okay, so, no? So, yeah, no, not the hydride. So this is, okay, so basically what you're going to do is you're going to hydrolyze it, right? So you're going to basically take this ester. If I treat it to acid and water, what's going to happen? I'm going to get the carboxylic acid. And what's special about this carboxylic acid that we talked about last class?
We can decarboxylate.
Do a decarboxylation, right? So then you heat it,
Right.
and what happens is you lose carbon dioxide gas. And so one of the advantages to the molecules that you can make from a Claisen condensations is that the products that are formed can be also sort of nice surrogates for the aldol reaction because, first of all, they can be deprotonated a lot easier, right? So you don't necessarily need to use LDA for something like this. You can get away with much more mild, like I said, like something like sodium bicarbonate or something like that. And then you can simply just chew off the carbon dioxide afterwards, okay? All right, so we got about a little under 10 minutes left.
Next class is just for you.
Yeah, we've only got 2 more classes left before we got 1 class and then the exam.
So the exam.
Yeah. So let me just finish up really quickly because so that we don't have to cover anything next week and we can actually do a review next class. So the one other class of one other class of nucleophiles that I want to sort of discuss is imines. Okay, so you can actually take so if you had, for example, right, so if you took this sort of cyclic amine, right, and you treated it with this ketone, right, what happens when these two react together? Right, we form the enamine, right? So we talked about this a couple weeks ago. Right, you guys gotta know this, right? And so this is basically this is an enamine. Okay, and it's basically like the enol, right? It's basically the nitrogen equivalent of the enol. Except the difference is the enamine is stuck at the enamine. The enol, so there's two differences, right? First of all, the enamine is kind of, it doesn't have to deal with that tautomerization, right? The enol is the minor tautomeric form, right? The enamine is the, you can't, it's not going to go the reverse, right? It's kind of trapped there. The other difference is that nitrogen is a better donor, right, than an oxygen, right? Nitrogen is more likely to be able to take on a positive charge, right, than an oxygen. And so for these same reasons, so enamines are commonly used to facilitate aldol chemistry and electrophilic chemistry as well. So again, if you took this, I'll just see E+, right, some sort of electrophilic source. It could be a Michael acceptor, it could be an aldehyde, it could be an alkyl halide. What's going to happen is you're going to attack that. Right? You're going to get to the iminium, and under the appropriate conditions, what can happen is that iminium will then hydrolyze under an aqueous environment. So if you did this, say for example, with a little bit of water around, right? Once it gets to that iminium after it traps it, that's going to hydrolyze. And you're going to get back to that ketone. Okay? So these sort of enamines are potentially very useful. Where enamines are particularly valuable is in the, there's a lot of areas, but one place that I think it's particularly valuable is in the area of asymmetric catalysis. You guys heard the term asymmetric catalysis? Right? So asymmetric catalysis is the idea of taking something that's basically non-chiral. This is the exact definition of it, but at least one example would be you take something that's achiral or doesn't have absolute stereochemistry, and you convert it into something that is a single enantiomer. Right? So you learned about how stereochemistry is so important, and so having molecules that are only, if you have a molecule that's chiral, you'd like to be able to synthesize only one of those two enantiomers, right? So this is something that's very, very important, for example, in drug development, for all the reasons that you learned about last semester. This molecule is very similar to proline. Right, so this is proline. And so proline is obviously is an amino acid, it's chiral. Proline can also be, because you have this carboxylic acid, you can imagine that you can convert that into lots of other things, right? For example, there's catalysts where people have modified these to be these big, bulky groups, right? And what that means is that once it condenses, right, you have some big, bulky group, or potentially a hydrogen bonding group if you want to leave the carboxylic acid there. But the point is that you have stereochemistry, and part of that stereochemistry can then influence this reaction over here, right? So, for example, I haven't really shown this with stereochemistry, but if we had, say, for example, stereochemistry, right, you can basically use this to relay the stereochemistry here, right? So, the stereochemistry here can be relayed based upon nucleophilic attack. Again, if it's sterics, right, you can imagine that if the sterics are over there, the electrophile is going to come from the backside, and you'll get that coming from the, well, I guess I twisted it around, but the approach will come from the back. And what's also interesting about this is I talk about catalysis. You'll notice that at the end of this process, as I've sort of outlined it, you're sort of losing that amine. And so it turns out that you can actually run this reaction with these types of chemistry and these types of reactions people have worked out where you can take catalytic amounts of these molecules and it can turn over multiple times, and that's where the catalysis comes in, because it'll form the amine, do the chemistry, fall off, re-engage with another carbonyl, do the chemistry, re-engage. And so, you know, the book talks about enamine chemistry, for example, nice ways to react with various electrophiles. When I think of enamine chemistry, this is what I think of, because it's such an important and powerful area. Enamine chemistry is some of the earliest examples of sort of asymmetric catalysis, and specifically organocatalysis, so catalysis based upon organic molecules. Neil?
Where did you get that extra carbon?
I just added it to put a stereocenter there. I added it after I was talking about it, just because I wanted to show a point of chirality. So, all right. Okay. So, any questions? Okay. So, for the exam sounds like it's 2 weeks away.
Week and a half.
Week and a half. Is it a Monday or is it Wednesday?
What's the Wednesday?
What do I know? I'm just. I don't. Whatever it is, whatever day it is, there's a holiday. So it's a Monday. Okay. So it's a Monday. So it's a week and a half away. So we have class no Monday, Wednesday. So next Wednesday we will have a sort of a review session. You're going to be responsible for everything that we've covered through today. Okay, so that's what's going to be covered.
You didn't really go over any
That's it.
like in the chapter.